Exercise 5.9 is asking you to locate each of the chiral centers in these molecules and identify the configuration of each one. So first, what does that mean, that word chiral? It really just means handed. It's coming from the Greek word for hand. And if you look at your hand has 4 sides. It has a palm, a back, a thumb, and a pinky side. Now, it's just a phenomenon of geometry that anything that has 4 different sides comes in 2 versions, a left-handed version and a right-handed version, just like your hands. Your hands look really similar. They both have the same back, the same palm, the same thumb, and the same pinky, but they're oriented differently in space. And you can get a sense of just how different your hands are by if you ever try to put your right hand in a left-handed glove. It won't fit. And so when you have something that has 4 different sides, it comes in 2 versions, a left-handed version and a right-handed version, and those versions fit into pockets differently, just like your right hand and left hand fit differently into a left-handed glove. Now, in this discussion so far, we've been fitting hands into gloves, but atoms can also have 4 sides, especially carbon, which forms 4 bonds. If it's bonded to 4 different groups, then it has 4 different sides, like your hand. And it will come in 2 versions, a left-handed version and a right-handed version. And those 2 versions fit into enzyme pockets and receptor sites differently, just like your hands fit into gloves differently. So the handedness of these atoms is going to be really significant because it determines whether a molecule will act as a chemical messenger or not in living things. For sometimes 2 molecules are exactly the same, except one is the left-hand version, the other is the right-hand version, and they'll smell different. So, for example, the smell of spearmint and the smell of caraway seeds, the seeds that are in rye bread, those are the same molecule, just one is the left-hand version, the other is the right-hand version. And in other cases, it can be more serious. In the case of thalidomide, that was a drug that used to be used to treat nausea, morning sickness in pregnant women. Well, one of the hands did that. The other hand version created birth defects, and so children were being born with deformed limbs. So the handedness of these atoms that are connected to 4 different things can make a gigantic difference in the way the atom and the molecule attached to it behaves. So it's important to be able to say which hand you have, the right-hand version or the left-hand version, because that tells you how that is going to fit into pockets, and so how it's going to behave. Now, there are rules for determining whether you have the right or left-hand version. Those rules were developed by 3 scientists, Kahn, Ingold, and Prelog, so they're called the CIP rules. And there are a few steps. The first step is to assign groups, the 4 different groups that are attached to the chiral center, to assign those priorities to those based on their atomic number. Now, remember, the atomic number is the number at the top of the box in the periodic table. The atom that has the highest atomic number gets the priority of 1, and an atom that has the lowest atomic number of the 4 gets the priority of 4. You always need to make sure that 4 is going away. That's with the dashed wedge. And if it's not going away, we'll talk about what you do when we get there. And once you have that, you go from priority number 1 to priority number 2 to priority number 3. And if by doing that you go clockwise, then you have the right-handed version of the molecule, which is called R. And you can remember that because going from the top to the bottom of an R, you have to go clockwise. If going from 1 to 2 to 3, ignoring 4, going from 1 to 2 to 3, you go counterclockwise, then you have the left-hand version of the molecule, and that's called S for the Latin word for left, sinister. So, and you can remember that because going from the top to the bottom of an S, you go counterclockwise. So these are the rules we're going to be applying in these examples here. Now, really, if you have the time, you should go through each atom in a molecule and ask yourself, is it bonded to 4 different things, one by one? And there are a couple tricks that can help you with that. For example, if a carbon ever has a double bond, then it can only, at most, be bonded to 3 different things, because carbon can only form 4 bonds total, and it's using two bonds to go to one thing. That means it only has 2 bonds left, so it can only bond to a total of 3 different things. So carbons in double bonds will never be chiral. Usually the chiral centers will stand out because they'll have solid wedges or dashes in them. Those solid wedges and dashes are telling you about the 3-dimensional arrangement of the molecule, and that's important when you need to know the handedness of it, the right or left hand version of it. So that's if you see those 3-dimensional bonds, solid wedges or the dashed wedges, it's a sign that you should be on the lookout that might be a chiral center that bond is attached to. So let's look. Let's see. When you're trying to identify chiral centers, you think globally. So let's try to think about whether this carbon here is a chiral center or not. Well, we have one thing to the left. We have the benzene ring. The 6-membered ring with alternating single and double bonds, that's benzene. So that's to the left. And now we know, after we've studied resonance, that actually those are all 1.5 bonds. So those conjugated pi bonds in a ring. So that's one thing. We have the OH and OH going up. That's a second thing. Notice how I'm looking globally here. I'm not just looking at one atom, but the whole group. I have this weird thing on the right. It's definitely different from the other 3 things. And the last thing I have is a hydrogen. Now, whenever you have a tetrahedral molecule, you're going to have 2 bonds that are in the plane. Those will just be drawn as lines. One bond that's coming out at you, and another bond that's going away. Now, this has to be a hydrogen because it wasn't drawn in, and the only atom you don't draw, the only atom that is implied and can be invisible is a hydrogen. And so that is our 4th thing. So that atom is bonded to 4 different things. And so like your hand, it has 4 different sides, and it will come in 2 versions, a left-handed version and a right-handed version. Those will fit into pockets differently and behave differently and make living things respond differently to them. So we have to know what hand we have. So when you're trying to identify chiral centers, you think globally. But when you're trying to identify whether you have the right or left hand, the R or S version of the chiral center, you want to think locally. Think about the atom that's immediately attached to the chiral center. And I'm going to write the atomic numbers next to each of these. So to the left we have carbon. The atomic number for carbon is 6. If you look on top of the box in the periodic table, for that you'll see a 6 there. Oxygen, the atomic number is 8. Hydrogen, the atomic number is 1. And the carbon on the right, the atomic number is 6. Now we can see that 8 is the highest number. So 8 is going to get a priority of 1. Highest number gets the highest priority. Hydrogen has the lowest number, so it's going to get the lowest priority, a priority of 4. The 2 carbons tie. If atoms ever tie, what you want to do is make a table. So I'm going to make a little table for this carbon over here and a table for this other carbon on the right. Now, if you go backwards, both of the atoms will just go back to the chiral centers, and that's not going to help you tell them apart. So you want to see what 3 things those atoms are bonded to going away from the chiral center. The carbon on the left, this carbon here, is bonded to a carbon, and the pi bond counts as a second bond to a carbon. So I'm going to list those in order of descending atomic number. Now those are all the same, so it doesn't matter. It's just carbon, carbon, and carbon. If I look at the right, the carbon at the right, this is bonded going away from the chiral center. It's bonded to a nitrogen, a carbon, and an invisible implied hydrogen. I'm going to put those in order of descending atomic number. Nitrogen has the highest atomic number, 7, then carbon, which has the next highest atomic number 6, and then hydrogen, which has the lowest atomic number 1. So now that we have these two tables, we can compare them. And we want to compare them one row at a time. You don't look at the whole row, you just look at the top of the, you don't look at all three of the rows, you just look at the top row, and only if that ties would you go to the second row. But you can see it doesn't tie. The carbon on the right is bonded to a nitrogen, and that has a higher atomic number than the carbon in the other, on the other side. And so this right branch is going to have the second highest priority. And the branch on the left, the carbon on the left, that'll have the third highest priority. So that's the first step, assigning priorities based on atomic number. The second step is to make sure 4 is going away, and conveniently it is here. We'll talk about what to do if it's not when that comes up. So if 4 is going away, we basically can ignore it, and we're going to go from carbon number 1 to carbon number 2, carbon number 1 to carbon number 2 to carbon number 3. And as you can see, doing that is clockwise. And if you go clockwise, then the handedness of that molecule is right-handed. So this is the R configuration. That is the right-handed version of that arrangement of pieces, molecular pieces. So that chiral center is going to be R. But that isn't the only chiral center in the molecule. If you look right next door, we have another chiral center right there. Now when you're identifying chiral centers, you think globally. To the right, we have this amine, that nitrogen there. At the bottom, we have a methyl group. To the left, we have a gigantic weird thing with an alcohol, the OH, and with a benzene ring. So those are 3 things, and then the fourth thing is an invisible hydrogen. Now, whenever you have a tetrahedral atom, a carbon with all single bonds, 2 of the bonds will be in the plane, 1 will be coming out at you, and the other will be going away. So I know that this hydrogen is going to be going away from me, because we already have the 2 bonds in the plane and the 1 coming out at us. So the other one has to be going away. So there's our fourth thing. So that atom with the red star is bonded to 4 different things, so it has 4 different sides like your hand. So it's handed, it's chiral, and it will come in 2 versions, a left-handed version and a right-handed version, and those versions will fit into pockets differently and behave differently in living things, communicate different messages in living things. So here, the first thing we want to do is to assign priorities based on atomic number. So I'm going to write the atomic numbers next to each of the atoms. When you're identifying chiral centers, you think globally, but when you're assigning R and S configurations, you think very locally, 1 atom at a time. So we look at just this nitrogen, that has an atomic number of 7. Hydrogen, an atomic number of 1. Carbon, an atomic number of 6. Carbon, an atomic number of 6. Well, nitrogen has the highest atomic number, 7, so that's going to get the highest priority of 1. Hydrogen has the lowest atomic number, 1, so it's going to get the lowest priority, a priority of 4. The other 2 atoms are both carbon, so they tie. And whenever atoms tie, you make a table. So this carbon at the bottom, I'll make a table for that. This carbon here, I'll make a table for that. Now you don't want to go back, you don't want to look going back. Going back, both of those atoms just go back to the chiral center. That doesn't help you tell them apart. What you want to do is look going forward. What 3 things are each of these carbons bonded to? So going away from the chiral center, this carbon here is bonded to 3 invisible hydrogens. So I'm going to list those in my table in order of descending atomic number. All of those tie, so it doesn't matter. For the other carbon, what 3 things is that bonded to? Well, that's bonded to an oxygen, a carbon, and an invisible hydrogen. So I'm going to put those in descending atomic number. Oxygen has the highest atomic number of 8, then carbon, which is 6, and then hydrogen, which is 1. So once you have these tables, you don't compare them all 3 rows at a time. You just look at one row, and only if the top row ties do you go down to the second row. But here they don't tie. The oxygen has a higher atomic number than the hydrogen, and so the carbon that's bonded to the oxygen will have the higher atomic number, higher priority than the other carbon. So now we've done that first step. We've assigned priorities based on atomic number, and the second step is to make sure that number 4 is going away. Well, here, luckily again, it is. We can talk about what to do if it's coming out at you or if it's in the plane when we get there, when we see that in a molecule. For now, we can ignore carbon 4, and we can go from carbon number 1 to carbon number 2 to carbon number 3. And notice here, when we do that, we go counterclockwise. That means that this handedness is left-handed. This chiral atom is the left-hand version of itself. And so we would write S. So those are the 2 chiral configurations for these 2 chiral centers. They're the only 2 chiral centers in the molecule. The one on the left is R, the one on the right is S. So let's try going through, so that's for ephedrine. And you'll notice almost every molecule in the human body is chiral. Sugars have a whole bunch of chiral centers. Amino acids, almost all have chiral centers except for one, glycine. And triglycerides even have a chiral center. So almost every molecule in the human body is chiral, handed, either a left or right-hand version. And so you'll see that a lot of molecules that are biologically active are also handed in order to be able to fit into pockets in a handed environment. So they'll have a lot of these chiral centers that are either R or S in them. And this is the case for ephedrine. Let's try that with one more for this video, and then we'll leave the others for another video, just so that the videos don't become unduly long. So here we'd look for chiral centers, and the big giveaway is when you have these 3-dimensional orientations. So when you see those, you should always check, at least, is that a chiral center? Well, is it bonded to 4 different things? It's bonded to a CH2Br, that's one thing. It's bonded to a chlorine, definitely a second thing. It's bonded to this weird group over here with a double bond. And it's bonded to this long carbon chain with a chlorine and a bromine on it. So those are definitely 4 different things. When you're identifying chiral centers, you think globally. So that carbon is bonded to 4 different things, and so it is chiral. It's handed, and it's going to come in 2 versions, a left-handed version and a right-handed version that will communicate different messages. So here, let's figure out which of these handed versions this is. Is this the left-handed version or the right-handed version? So the first thing to do is to assign priorities based on atomic number. Now, the atomic number for chlorine is 17. The atomic number for bromine is 35. Oops, sorry. When you are assigning these priorities, you're thinking very locally, so you're just thinking about the atom that's immediately attached to the chiral center. So the one that's attached here is actually the carbon, and the atomic number for that is 6. To the right, we have another carbon with an atomic number of 6, and to the left, another carbon with an atomic number of 6. Well, we know that chlorine definitely has the highest atomic number of these, and so it has the highest priority, a priority of 1. The other 3 tie, though, and whenever atoms tie, you want to make a little table. So we have a carbon here, and a carbon here, and each of those tie so they each get their own table. Now, when you compare these, you don't want to go backwards because they all go back to the chiral center, and that doesn't help you tell them apart. What will help you tell them apart are what they're bonded to going away from the chiral center. So this carbon at the top, that's bonded to a bromine and 2 invisible hydrogens. So we want to list those in order of descending atomic number in our little table. So bromine has the highest atomic number, and then the 2 invisible hydrogens. For the carbon at the right, that carbon is bonded to a carbon and 2 invisible hydrogens. So we'll put that in order of descending atomic number. And for the carbon at the left, that's bonded to a chlorine and a carbon twice. So that's like 2 carbons. So chlorine has the highest atomic number there, and then 2 carbons. Now when you compare these, you never look at all 3 rows at the same time. You compare just the top row, and only if that ties would you go down to the second row. But none of these do tie. Bromine, with an atomic number of 35, has the highest atomic number, and so the carbon that's attached to that bromine will have the highest priority of these 3. Chlorine has the next highest atomic number of 17, and so the carbon that's bonded to the chlorine will have the next highest priority. And so that means this last carbon is going to be carbon number 4. So that's the first step, assigning priorities based on atomic number. The second step is to make sure that number 4 is going away. Now here it's not. This is actually the most difficult case. The easiest case is if 4 is going away. Then we can just go straight to the third step. See whether we're going clockwise or counterclockwise when we go from 1 to 2 to 3. But here, the most difficult case is when 4 is in the plane. So it's represented by just a regular line. When that's the case, then you want to switch number 4 with the branch that's going away. So I'm going to redraw this molecule. And actually, instead of drawing the whole thing, I'm going to just write a chiral center here, so like an atom here, and I know that I have 1 here, 3 here, 4 here, and 2 here. So I'm going to switch 2 and 4. Oops, because I want 4 to be going away. And right now, 2 is the one that's going away. So I'm going to switch those 2. So it goes like that. So now 4 is going away. But whenever you switch 2 branches, you switch the chiral configuration. So if it was R, when you switch them, now it's S. If it was S, when you switch them, now it's R. So to get them back, I'm going to switch any other 2 of these branches. It doesn't matter which 2. I'm going to switch 1 and 3. So now that we've switched these, I'm going to use my little diagram. 4 is going away because I put it up here. And I'm going to go from 1 to 2 to 3, ignoring 4. And notice that when I do that, I'm going counterclockwise. And if you're going counterclockwise, then you are left-handed. You are the S, or left-handed version of the chiral center. So this chiral configuration here is S. So I'm going to write that in there. The other chiral center that we have is where the other bromine is attached. So it's right here. And that is bonded to 4 things. You can see it's bonded to a weird sort of branch with the chlorine on the left. It has the bromine at the bottom. It has a wild and crazy group to the left. And you have a hydrogen, an invisible implied hydrogen, which is coming out at you. Remember, whenever you have a tetrahedral carbon, you have two bonds that are in the plane, one going away from you, and another one coming out at you. So this last carbon, or this last atom, is a hydrogen, which is coming out at us. So that's our fourth thing. And because that carbon is bonded to four different things, it has four sides, like your hand, so it's handed or chiral. And we need to know which hand is here. Is it the left-handed version or the right-handed version? Because those two will behave differently by fitting into different pockets. So the first step is to assign priorities based on atomic number. Now, the atomic number for carbon is 6, the atomic number for hydrogen is 1, the atomic number for bromine is 35, and the atomic number for carbon is 6. So immediately we can see that bromine has the highest atomic number, so it's going to get the highest priority of 1. Hydrogen has the lowest atomic number, so it's going to get the lowest priority of 4. And the two carbons tie. Now, whenever atoms tie, make a table. We're going to look at what three things these carbons are bonded to going away from the chiral center. So this carbon on the left is bonded to a chlorine, a carbon, and a carbon. And I'm put those in order of descending atomic number. So chlorine comes on the top because it has an atomic number of 17, while the carbons only have an atomic number of 6. This carbon on the left is bonded to a carbon and two hydrogens. The carbon goes on top because it has the highest atomic number of those three. Notice we didn't go back to the chiral center because that ties for both of these carbons. That's not going to help us tell them apart. So when you compare these little tables, you don't look at the whole table at once, you just look at the top row. Only if that top row ties would you go and compare the second row. And only if the second row ties would you look at the third row. But here that top row doesn't tie. The carbon on the left is bonded to a chlorine, and chlorine has a higher priority than carbon. So the carbon that's bonded to the chlorine has a higher priority, and that gets the number 2. And the other carbon is going to have a priority of 3. So that's the first step, assigning priorities based on atomic number. Then, once we have that, we need to make sure 4 is going away. It's not. Here's what you do when 4 is coming out at you, like it is here. We saw that when 4 is going away, you have to switch 2 groups. When 4 is coming out at you, ignore 4, go from 1 to 2 to 3. You would think that the configuration here would be S because it's counterclockwise. But because 4 is coming out at you, you switch it. So instead of S, the configuration for that will be R. And the only reason you're switching it is because 4 is coming out at you. So the configuration for this chiral center here, the handedness, is R. This is the right-hand version of itself. And so in this biologically active molecule, this anti-tumor agent, a lot of really interesting molecules are made from sponges and from corals, marine organisms in general. And as we've seen before, almost every biological molecule has some sort of chiral center. It's a really common feature. And in this one, we have 2. We have a left-handed version on the left, and we have a right-handed version on the right. So we have those 2 hands in this molecule. And that will affect what type of pockets this molecule fits into and what kind of messages